Hi, welcome to day 6 of 100 days of Common Lisp. Today's video is going to be a bit different. We are not going to solve a problem. I think the problem in the original was easy. I didn't add anything new. So instead today we are going to look into a bit of theory. So firstly I'll talk about if Common Lisp is a functional programming language or not. And but more importantly, we'll look at concepts. Let's get started. So if I just lay out a few common programming styles and their languages, representative languages, this is what it would look like. So everybody starts out learning a procedural or imperative language, things like C or Python. And then some people go on to learn object-oriented programming. That's usually like the second thing that someone learns. And common examples here are C++ and Java. But usually this is where typical programmer education kind of ends. Some people out of interest kind of go and explore and then learn about other categories, things like functional programming, actor programming, logic programming, and so on. Here are a few examples like Haskell for functional programming. But a large part of this remains a bit mysterious to most programmers. So me included. So when I started, I assumed that anything that was not really either of these had to be functional. Like I wasn't really aware of these categories, and I just assumed when I heard about Lisp that Lisp was functional. I mean, Lisp does support functional programming, but it's not really a functional programming language. So what I mean by that is Common Lisp is actually a multi-paradigm language, right? It can support many of these, if not all, and that's the really interesting part. There are other multi-paradigm languages. For example, Scala is one, but obviously our interest is with Common Lisp, and multiple multi-paradigm languages actually become difficult to learn because there are different styles, and it's like trying to learn multiple things at the same time. So if your interest is actually in functional programming, the real functional programming, then I would recommend you not go via Common Lisp, but go via some other paths. So again, I mean, you can always do functional programming in Common Lisp, but those are two different things, right? Common Lisp is not equal to functional programming. So what are your options here, right? If you just want utter basics, things like lambdas and function application, things like map, reduce, you may very well do it in base languages like Python or JavaScript. Now, that's okay, but it's not really learning functional programming. So if you want to actually learn functional programming, then my recommendation is to go with standard ML, which is surprisingly a kind of forgotten language, not really well known, but it's a very small language. Much like what Go is, you can pick up the core concepts like within a single day and really get going. So it has all of the core functional programming constructs like type systems, algebraic data types, functors, and so on. There are multiple compilers. I have used these and I've had a good experience. Now, the good benefit of knowing standard ML is you can switch eventually from standard ML to OCaml, which is also a bit of a multi-paradigm in the sense it is kind of suitable for other things like systems programming and not just pure FP. Now, if you really want the purest form of functional programming, then you should go with Haskell, right? There is no other simple solution here. It's a lot of work. It has the most purest form of FP in terms of state and lazy evaluation and so on. But that is it. Now, if you would like to go for a Lisp-like language or a Lisp and also learn FP, that is assuming you know one of these concepts, then a good option for you is Scheme. There are many schemes that exist. I mean, commonly Racket is recommended, but you can really try any of the schemes. I have a soft spot for Gerbil scheme, which is a very nice batteries included language with a lot of cool features. Now, if you want even more better FP route, I would recommend Clojure because it has immutable data structures and so on. For example, we don't really have these in Common Lisp, and if your aim is FP with Lisp-like syntax, you might as well go with Clone. Now, all this said and done, why do we come back to Common Lisp, right? I mean, if it's not functional programming, then what are things that Common Lisp has that others don't? And I would say really these are the few kind of key features. Macros, which underpin everything. So maybe a better word to use here is meta programming. And we'll see in our videos how powerful macros are. The other aspect is this whole interactive development in Common Lisp, completely different, unbeaten, and there I would just say there's literally no other language which can give you this kind of experience. So normally it's called a REPL. It's a bit confusing. This REPL is the one that is invented all the way back in 70s. We have REPLs in other languages today, but they are not really up to mark. As in, the kind of power and interactiveness you get from the Common Lisp REPL is different. By this I mean things like Slime. Again, we'll see this more in our videos. Yet another feature of Common Lisp is CLOS, Common Lisp Object System. Basically, Common Lisp is a cool OOP story, a kind of object-oriented programming which really is very different from the other common versions, and something known as a meta-object protocol. These are very advanced concepts. We'll cover them later, but you'll see exactly how cool these things are. And interestingly, clause was added to Lisp via macros. So it really shows you how you can add new advanced features to your system as libraries, as macros, even without the underlying system language not supporting it. Finally, I'll also call out Common Lisp condition system, which is a very advanced form of stack management during errors. Again, you have to see it to understand what it is. We'll do that later. So really, these are some of the things which make Common Lisp Common Lisp. It's a very different philosophy of computation. That's what I would say. It's not really, it's something new that you need to learn and experience. Now, I have this picture here of the Mazda Miata, the design of which was inspired by ancient Japanese cavalry. The philosophy really is that horse and rider as one. I haven't driven it, but this is what I hear. And I feel that the same analogy might be drawn to Common Lisp, where the user, the programmer, and the machine, the compiler, and the language are really one, right? There is a very smooth interaction between man and machine. Really, it's more like man and horse than a machine. But a better analogy, it's not going to be obviously as light as a Miata or a horse. And Common Lisp is more like an Imperial Star Destroyer. And that's a good analogy because not only is it so large and old, but there's a phrase I've heard somewhere which I think is very apt, that Lisp is a technology which somehow exists both in 1970s and 2170s. It's both old and alienishly new. Anyway, enough talking about generic stuff. Let's get to specifics of today. So what is a list, right? So we have seen again and again, Lisp is Lisp, Lisp is list. List is the core data structure. So what is really a list? Now, you might just think of linked lists, which are like commonly known in C or in other languages. The structure looks somewhat like this. You have your individual nodes, which have a data slot and a pointer, and the pointers point to other instances of the same node, right? So you see this a simple pseudocode version of this, the struct node with an item of some type, and then the node pointer to next. Now, a lot of people think cons, which is Lisp's fundamental unit, are like linked lists. And I like to kind of, I mean, they are similar, but I would like to refer to an old essay from Dijkstra. So I found this essay really very interesting aspect that has guided my thinking over the years. I would recommend you go read this essay in its entirety, but I want to highlight some things here, right? For example, he says the usual way we think about tomorrow is using yesterday's experience, right? And like it says here, it's the most common way to deal with novelty, right? By means of metaphors and analogy that we link to the new to the old, the novel to the familiar, right? And I think this definitely happens when people think about Lisp lists. They try to draw analogies to linked lists that they know, and then they just call it out there, right? But like the rest of this essay points out, the idea is to really think about new concepts from a fresh point of view, right? Or by looking at what is different from the older version. So, like he says here, right? Our past experience is no longer relevant. That analogies become too shallow, right? I mean, the analogy can still work. A common Lisp list is like a linked list, but just leaving it there, you don't really learn what actually makes it different or what actually makes it the fundamental unit of Lisp. So in the rest of the video today, we will look at exactly what a const cell is and what Lisp's lists are, right? So a const cell, like you might think of the analogy before, we have a linked list node, but instead of having a data section and a pointer, const cell is designed very differently. It has two pointers, right? Just think of it this way. The individual unit, the const cell, has two slots. It's usually called car and CDR. So this is an historical artifact of the name of the register on the machine that Lisp was developed in. But just think of it as two slots. And what do the slots point to, right? So that's better explained with this pseudocode again. So we have seen the word S expression again and again. I've used this to refer to our code, our lists in Lisp. So really an S expression can be thought of as a union of an atom or a const, right? An atom is an individual item like a number 1, 2, 3 or a single symbol. Let's worry about that later. An atom is an individual item, and the other option is a const, right? This const. And how is a const defined? A const itself is a pointer. It has two pointers, one to an S expression called char and another to an expression called CDR. So this is the fundamental unit. Look at this and contrast it with this. So please don't think that this node of a linked list is the same as a const. A const is very different. Now, with that basic, we have seen this a few times. A list 1, 2, 3 can be represented with a quoted list or using the function list. Internally, what this is actually this section or group of const cells. So the first const cell, the first pointer, the car of the first const cell as 1, the atom, and the second, the CDR, actually points to another const cell. And that const cell again has its car pointing to 2 and its CDR pointing to another cell. You can go all the way down until we come to the last section with entry, which is a nil. So this is actually equivalent. So what we see below here, the structure made of const is the same as this structure made of list. So we can look at this from the REPL if that makes it easier. So we have a list 1, 2, 3 like we've seen before. We also have a const. As you can see, const doesn't work with one argument, it needs two arguments. So we're going to abort this and we're going to call, you can see here the documentation showing up. So the second argument, yes, and this is a single const cell. Please note, this is not a list. This is a list. This is a single const cell. Now, you can just compare and contrast because I have created a const cell previously. I can also create a list with two items. So if I do this, this looks very similar, but it's not the same. This is a list, and internally this list, like we saw before, is made of multiple const cells, one after the other. So this is cell 1 with 1, and then cell 2 with 2. CDR of the first one points to the rest of the list. And this is our short notation for list, whereas a const 1, 2 is directly a single const cell with the car pointing to 1 and CDR pointing to 2. And in short, this is how it's represented as, see this dot, You see this dot here, you see this dot here also when we did it. So this is known as a dotted pair, and that shows that this is a concept. I can show you. Let's define this variable just for demonstration, and you can see car of A is 1, CDR of A is 2. Now a lot of times if I define this variable back to a list, so A is a list, and a lot of times when you get started with Lisp, one of the first functions you do with Lisp is car and car CDR on lists. In our series, I didn't do it very consciously in the first 5 episodes. So we have this, which will give us 1, if you understand, and CDR of A, which will give us the rest of the list. So CDR of A is actually another list, which is 2, 3, 4, 5. And I hope that it's very clear by looking at this diagram what's happening here, that the CDR of this list is actually this pointer, and that just points to this, right? So this whole thing is what you get when you look at the CDR of this list. And that happens to be yet another list, right? That's why your list A and the CDR of A is another list. Now, if you want to see this definition in action, how you make a list, how you build a list, right? So we do cons of 3, and because the last entry has to point to nothing, you have to use nil, and that makes it a list with 1 item. Now I can take the same list and prepend to this the other cell, where the second cell is that cons cell, and that makes it 2, 3. And we can do the same thing again if you want to just have parity. So 1, and this gives us the original list, which is A, right? So this is how we build lists internally. Now this is not of much use to you now, but this is the core structure that powers the whole structure and the whole design of Lisp.